Thank you very much. It's my great pleasure to be with you. I hope everyone can see the screen and can hear me. So that looks fine. Well, we just had an interesting discussion about solar eclipses. We had a fantastic talk about quantum optics this morning, so it's really hard for me to catch up with all of that, but I will try to do my very best and to share with you in the next hour or so Nanooptics and Plasmonics, some things we did here in Graz in recent years. And for reasons you will understand, as I hope, within some minutes, I gave it a subtitle, Probing Plasmons with Photons and Electrons. So just a brief orientation. We are a little bit more in the south now. I'm speaking to you here from Graz. I know you're not only in Brno, but all over Europe. So I think this is really a fantastic solution for the given circumstances. A short overview. Nanooptics and plasmonics are two things that I would like to introduce with some care. First of all, I leave it to our chairwoman then to decide if I should just take some questions here or answer some questions here once I have done the more fundamental introductory part. And then I would like to show you a few snapshots, a few examples, a few more or less recent results out of research that concerns different approaches, different methods, different experiments, so to say, for measuring optical phenomena on the nanoscale. And if I would wish you to take one particular message from my discussions, it's that you can use either light or photons or electrons to probe optical phenomena. This is something that is, I think, very exciting and that allows, of course, different channels to be approached, different venues to be opened, and to see more things than just with, for example, classical optical spectroscopy alone. Okay, let just these two images speak for why I am fascinated with optics, and I think many of you as well. Well, the right thing, this is not the place to talk about that. Of course, I'm also anxious to see what, for example, the Webster Space Telescope now, I think really to be launched late this year, is about to bring. But I would like to look on small scales, right? And to look first of all at how small a structure can be that we can image then by optical means. Well, conventionally, unfortunately, it's not so small. There is diffraction, as I'm sure all of you are aware of. Light is a wave phenomenon. We have diffraction, and if we use visible light to do microscopy, we are at a spatial resolution limit of, say, around 200 nanometers at the best. So I can simply tell these two structures here, one from the other, but I cannot do it here. And sure enough, there is an evident question. I'm sure some of you have looked into a microscope and increased the magnification, and there was some limit to what you could see in more detail. So is there a way around it? At first view, doesn't look too good, because if we just look at the diffraction patterns of two small objects, for example, two fluorescing molecules, there is this diffraction pattern having, of course, a finite extension. And if we bring them too close, the maxima here begin to overlap. Well, you could say maybe I can fit simply the maximum positions, but as here in real life, you don't really have nice signal to noise ratio like in these calculations as they are. So it looks much more noisy. There are fundamental limitations that you get from the granular structure of light. And you have simply too many fit parameters. And you know, if you have too many fit parameters, everything comes out. So apparently here, first view, 200 nanometers is our limit. Now, we could accept that. We can also argue that this is kind of backed by many different perspectives on diffraction. For example, you can simply use the uncertainty limit and find out that diffraction as we see it here, so that you have this blurred image is simply due to the uncertainty in lateral momentum because you have sent your light on a small structure. So the uncertainty limit is also behind that I would say further diminishes our prospects to overcome it. Now, you could argue, you know Huygens principle. Huygens principle says if you have a light wave that is propagating in space, let's say here from left to right, you can imagine, that's an important point, you can imagine that each and every point emits a spherical wave, and the envelope of all those spherical waves that propagate in space give you a new phase front. Now, this is clearly just a kind of model that you could, in terms of a Gedankenexperiment, apply to understand how, for example, the envelope of a wave in a kind of qualitative way is understood. But you could go on and say, wait a second, you know that each and every material is built from atoms, right? So maybe those atoms are something like Huygens principle in reality. Why could that be? Simply because the electric field of light interacting with atoms, say at the surface right here, is exerting a force on the electrons of the atoms and is thereby inducing dipoles. So you have dipole moments here, and these dipoles are okay, they oscillate with light frequencies, so at very high frequency. But we very well, all of us, know our dipole fields, and we know that our dipole fields are strongly inhomogeneous, and if each and every atom features a dipole field, sure enough, if now I could fly along this plane right here, okay, I would see a modulation of the local field strength. So we have two informations. Uncertainty limit, diffraction, everything tells us this is our spatial diffraction limit in optical microscopy. This small excursion, okay, just thinking a little bit how it could be different, tells us that light fields should be modulated very close to a surface in terms of, say, an angstrom or so. Clearly, both of those points of views, I would claim, are valid. So apparently something happens between very close to the surface and more or less far away from the surface where our classical microscope operates. Apparently, space is a low-pass filter for spatial frequency components. And very well, this indeed is the case and simply seen from the expression you all know for a plane wave. Let's say this is our Z position, the lateral positions are X and Y. So this is just the expression of a plane wave, nothing else, right? You have your wave vector components and you have your spatial coordinates X, Y, and Z. Now, if light interacts with matter, it picks up momentum, right? Momentum is, of course, only transferable in the direction where there is some modulation in the matter of its composition, and that's in the X and Y directions. So light picks up information from your sample in X and Y directions, and the smaller the structure is, the larger the wave number or the wave vector component. So the smaller X and Y components in real space, the larger this kx and ky, which is in inverse space. And you see what happens if structures become too small, kx and ky become larger and larger, and at a certain point, this expression under the square root becomes negative. And that's the full explanation we need. Of course, the point where it gets negative, sure enough, is nothing else than the diffraction limit. And what happens then is that if you have a negative expression under the square root, the kz becomes imaginary. Well, there is already another imaginary unit here. And from a homogeneous propagating wave, you switch to an exponentially decaying so-called evanescent wave. So that's the action of space, as I called it before, as a low-pass filter for spatial frequency components. What can we do about that? Well, there is a way to recover these evanescent waves by near-field optical microscopy. You can scatter back, or you can provide back the large kx and ky values to convert again these evanescent waves to propagating waves by, for example, something that is playing the same role as a small structure that generated them, namely the sharp tip of a near-field optical microscope. That scatters back the evanescent waves into propagating waves, and so just depending on the curvature or the spatial extension of the tip that you have here, that in principle works similar to a scanning tunneling microscope or a scanning force microscope. So scattering back and giving a spatial resolution now determined by the tip rather than by the wavelength that is involved. So that's basically optics beyond the diffraction limit and optics that, well, is due to evanescent waves. So nano-optics is all about evanescent waves. You have the summary here again. And what else is nano-optics? It's very often ultra-fast. You know, small structures are quite often, if you allow me this simple correlation, quite fast. It's quite often, necessarily not always, quite often in a quantum regime. You often look at simple emitters, as you have also seen in this morning. And now I come to the second part of my title. It's particularly bright with plasmonics. Plasmonics is the investigation, understanding, and sometimes application of the effects of surface plasmons, which are, well, resonances in small metal structures or on metal surfaces. I will come back to that in a minute. And if you go to small structures, of course, it's easier to investigate them if they are bright. And I think already from your gut feeling, you can argue that a small metal particle scatters light more strongly than a small dielectric particle. And indeed, here, for example, for gold particles, and the very famous case, as you always see in talks where plasmonics is involved, of stained glass windows, church windows, many of the colors, not all of them, but many of the colors that you see here in the stained glass windows come from the pure fact that you have these resonances, these plasmons in metal nanoparticles, and they scatter spectrally selective light. And it's not necessarily that you have to look at metal particles if you do optics on a small scale, but as I said, it's particularly bright because simply the effects are quite strong. And so this, just as a side remark, it's probably not a very big surprise that many of the things that have been done in nanoscale optics early on have very often been connected also to metal particles that simply absorb and scatter quite strongly. So this is the former head of the nano-optics group in Graz, Franz Auseneck, and as far as I, Wahid Sandoktar here know, he was one of the first, or maybe the first, who coined actually this term. Good. So how is that working? How are these plasmon effects in nanoparticles are working? So you know that if you go to small scales, many properties of matter, thermal properties, mechanic properties, electronic properties, of course, in the first place, they change. And sometimes they can change spectacularly. And I think also this here is a quite evident spectacular change. Now this is gold on the macro scale, on the centimeter scale. And this is scattered light from gold nanoparticles that you see here. Okay, they have slightly different shape, not so much, and you see they scatter light quite dramatically in different regimes of the visible spectrum. Now, why is this? Quite simply, and let me now emphasize that this is a purely classical description that I now apply. The electric component of the light field accelerates and thus separates the charges in a metal nanoparticle. the nanoparticle is finite, so you get surface charges. These surface charges induce to Coulomb attraction restoring force. You have some losses, so you have all the ingredients for a light-driven damped harmonic oscillator. So always when you hear in lectures that you get most of physics when you learn about your driven harmonic oscillator and combinations of your driven harmonic oscillator. Again, here, one point to support that view. You get a resonance. If you have a resonator, an oscillator, sorry, you get necessarily a resonance. And for many metals like noble metals, gold, silver, but also copper, aluminum, sodium, these resonances lie in the visible spectral range. It's a quite broad resonance, as we will see in some examples, well, because metallic damping is quite significant in general. What we call plasmons, I have to add or to correct, is in the correct use of the term, the quantum of the energy of this oscillation. So you see, I introduced plasmons as a purely classical effect, but in fact, if you look close, it's a quantized system, just like you have quantized magnitudes in phonons, for example, or in magnons, or in excitons, or wherever. But let's stick to our classical description and put a few numbers in, what you can do to better understand a little bit where the different terms and influences come from the material and from the shape, as we have already seen. I can simply write, as I do here, the polarizability of a small sphere. What does small mean in this case? It means so small that you can assume you have a quasi-static polarization of the particle. That simply means your wavelength is much larger than your particle, so that over the extension of your particle, your electric field that induces the charge separation is approximated as constant, right? So you have just this plus-minus charge separation, and that also gives you a few insights into coupling that comes along later on. If you have a dipole character, and if you're much smaller than the light wavelength as a particle, you can only have dipolar character. It's hard to couple to higher multiples and so on and so forth. But let's go back to this expression for a sphere. In this case, it's, as I said, the polarizability. You find, apart from a four factor that is basically the volume, the permittivity, okay, so refractive index squared, basically, of course, a complex quantity. The permittivity of your metal minus the permittivity of your surrounding, that might be vacuum, that might be water, that might be glass, over the permittivity of the metal plus 2 times the permittivity of your medium. So you see, it's indeed a quite simple expression, but what you already see right away is that if you have a permittivity value of -2 in vacuum, or -2 times the permittivity of the medium, here in the denominator, you have a resonance, simply because, well, this term here goes to 0, so the polarizability would be infinite if you wouldn't have the imaginary part to the rescue, of course. So no polarization catastrophe right here. And you see that you can only fulfill a resonance in polarizability, and thus a quite strong, a strong optical response if you choose a metal, okay? Highly doped semiconductor maybe, but a metal, because only then you get a negative value for the real part of your permittivity. So everything you have to do is to get a table for, let's say you're interested in copper, and you look where actually the real part of the permittivity is -2 if you're in vacuum, so epsilon medium is 1, and here you go with a resonance frequency for your polarizability. Now, The polarizability, of course, is something that is not directly measured, but as you see here, it immediately leads you to observable quantities, and those observable quantities are simply scattering and absorption, here expressed as cross sections, okay? And you see that the imaginary part of your permittivity simply gives you the absorption cross section, and a 4-factor times the polarizability squared gives you the scattering cross section. You can already learn a lot from those expressions. Small particles being here with a small volume give rise rather to absorption than to scattering. If you get larger particles here on the scattering, the volume impacts with a square. Okay, so then scattering takes over. You have this k to the 4 value here in scattering. Should have to do something with the fact that the sky is blue and some other effects. So these are usually the quantities you can observe. Now, if you're not happy with spending your whole life here with a sphere, of course, more elaborate shapes, nowadays we basically all the time calculate them with numerical methods, but you can go on to get a feeling for everything with an extension of this sphere to other shapes, to ellipsoids that are well fitted to approximate all kinds of shapes. And you see you can stick to the simple expression that you had up here, almost as simple, and you put all the complications of the length ratio of your ellipsoid approximating the shapes that you're interested in a shape factor. That is basically, let's call it a number between 0 and 1. So that's, I think, a tour de force, or has been a tour de force through what you can see, what you can expect from the scattering and the absorption based on the polarization of a small particle. Of course, there's more to the story. We can now look at the combination of, let's say, a molecule or a quantum dot or NV center, whatever. You remember this morning's presentation. And you can ask what happens either in exciting, let's say, a molecule, or in looking at the emission of the molecule. If I put it in a neighborhood of a particle. Okay, it might look like this, a nanoparticle, it might look like that. That's details are not so important here. Well, in the excitation channel, here expressed as a rate, you can simply estimate that you have a stronger local field. Why is that? We have a resonance, and if you are in or close to resonance, the electromagnetic field, the near field around this particle, gets resonantly enhanced. That means you have simply a stronger local electric field and electric field density. Well, and that pushes, of course, your excitation. Maybe this is the aspect that is not so super exciting in many cases because, well, you could take a better lens and focus more light on a molecule. What's probably more exciting is the emission rate. The emission rate is also boosted by the field enhancement. Of course, if you emit light, it's not the field itself of the nanoparticle that is not there yet, that is the decisive quantity, but it's the other side of the medal, so to say. It's the local density of states. So the local density of states, the photonic local density of states, simply tells you how much light you can squeeze into all the possible excitations that are there in the system. And you see the higher this local density of states is, the higher the excitation rate. And again, here you already saw examples for that this morning. I could call it just as a catchword lifetime engineering, so you can boost or reduce the lifetime of an excited system or of a quantum emitter. Okay. So after all these formulas, let's relax just a little bit. Here again, just because I think it's really, really nice, you see again nanoparticles that were chemically fabricated in this case. Apparently, you see they have different color, so they scatter light in a different spectral regime. And from what we learned, we can already think that, well, they have different shapes. Or that could be, a priori, it could also be they consist of different material, which is not the case. That's all gold here in this case. So they have different geometries in this case. Now, you can have a closer look. And this is nothing actually that came along in the last years. This is also nothing that came along in the last decades. This is over 100 years old. Part of it was also done here in Graz. It was Mr. Richard Zsigmondy, who not only fabricated particles like that, okay, colloid chemistry, it was called at that time, still around nowadays. And well, unfortunately, I don't have a better view on the microscope he has here. But if you have asked yourself, why is it that we can see these particles so brightly? Well, I told you, scattering of metal particles is bright. But of course, if you use your optical microscope in the standard configuration, looking at either transmission or reflection images, you wouldn't really see a lot, because simply the background light, the light that goes through or is reflected, just unaffected by the rather small particles, would cover most of it. So it's always a good idea, if you measure small quantity, to do it from a zero line that is really zero in this case. And therefore, Richard Zsigmondy developed dark field microscopy. So I think in this case, simply this is a light condenser, shining light here parallel to the table plane. And that means if there is no sample under the microscope, you see nothing. Okay, that's the zero I was talking about. And then if one of the particles scatters light, you have its signal just before zero background. Of course, still nowadays, very, very convenient, because with a configuration like that, you can simply let the exposure of your CCD, CMOS, or whatever run and collect photons galore, so that you get images like that. But dark field microscopy goes back a long time. What we like to do today is still use nanoparticles that come out of chemical synthesis. They are excellent, and the colleagues from chemistry are really developing lots of things, crazy shapes. The biggest advantage is the excellent material quality of those chemically synthesized particles, right? So you can have them, most of them are single crystalline. They are atomically flat on the surface. You can also switch to fabrication methods like lithographic electron beam lithography mainly, or ion beam lithography. Then you can shape your particles at will, but usually the price you pay is that you have some roughness, of course, at the surface, and because these fabrication schemes involve deposition, vapor deposition, usually physical vapor deposition steps. They are also polycrystalline in many cases, but there is a wide range of methods that you can apply to choose from. Good. I have talked so long about that here, right? About one nanoparticle. And I have argued that you have these local resonances that are basically dipolar excitations and all the effects that are connected with that. You can, of course, add particles, you can couple them, you can look at coupling effects, what actually happens. But, and that's now the main point I want to make with this slide, that there is a full family of surface plasmon modes that is not at all constricted to the dipolar excitation in a nanoparticle. You can have a cylindrical geometry, for example, and you can propagate plasmons along this cylinder, because there is no light field at the inside. This corresponds, like in a dielectric waveguide, that corresponds to a freely propagating wave. You have exponential decaying functions at the outside and at the inside, and that's why you can make the lateral extension of such a plasmonic waveguide as small as you want. Be aware, nevertheless, that damping, metal damping, severely restricts the distance you can cover with these propagations. Then you can go on surfaces. You can, of course, also put structures or dielectric superstrates on your surface. But the most maybe well-known plasmon mode is the surface plasmon mode, at least in the optics community, where you now have something that resembles very locally this dipolar character from the particle, but which is in fact delocalized as a propagating wave, a true surface wave over this metal dielectric interface. You see here a sketch of the longitudinal character as it is. So you have this plus minus charge separations along the propagation direction. You have the exponentially decaying evanescent character fields on both sides of the interface. And here maybe for the specialists who've already heard about that, this is a so-called dispersion relationship showing you the k vector that we were already discussing in the energy or momentum and frequency or momentum and energy. So this is light, right? The light line right here, and the surface plasmons are always to the right of the light line. So for each and every frequency that you have higher momentum. And this calls for specific methods, a grating, for example, to couple light to plasmons, but nevertheless, this is feasible and is applied in many cases. Okay, maybe let's ask the chairwoman, what about brief questions, or if there are any, or if we shouldn't do it and only at the end, just as you like?
I guess we could. Is there any question in the audience? Please feel free to write it in the chat or maybe raise your hand and you can use the mic as well. If not, I would have a short one. A few slides back, you were showing these gold nanoparticles which had different shapes and exhibited different colors. What was the polarization of the illumination in there? Yes, exactly this picture in the bottom right corner.
Right. It was non-polarized in this case, yeah.
Mm-hmm.
It always depends if you have the small structures. Well, I'm not sure for the blue one, actually. For the other ones, I'm sure. It depends how many different modes you can have in there, okay? And of course, if you begin to mix up an excitation along the long axis and one along the short axis, you will blur the color that you have in there. So I have to admit, in this case, I'm not sure. Okay, in the other ones, this was just a dark field setup that was non-polarized in these cases.
Okay, I can't see any questions from the chat, so probably everyone's satisfied with your lecture for now. So maybe you can continue.
Okay, this I want to add just very, very quickly before we now jump to our examples, a few words on why. So I sincerely hope you found it in principle interesting, but let me just briefly outline why are we doing that, or why are other people doing that? Well, first of all, of course, you want to improve spatial resolution. There is lots of interest. Of course, which you can do, or let's say could do with near-field microscopy, because near-field microscopy is fantastic and we use it in the lab a lot. But arguably, it's not a tool that has reached broad application because it's cumbersome, it's complicated, and it's, well, not always really meeting the expectations, so to say. There is a method in high resolution that got the Nobel Prize in chemistry, interestingly for me. Super resolved fluorescence microscopy. Why was this in chemistry? Well, of course, the molecules that you need for that come from there, and the application of this microscopy method goes in the direction of where are optical microscopes mainly used? Well, chemistry, biochemistry, biomedicine, biomolecular applications. Small structures looking at sub-wavelength behavior could be interesting to get novel approaches per se in optics and photonics, not necessarily in all parts and all applications, but as you have seen again this morning in quantum optics, looking at individual emitters, making some structures at least small, could be appealing. To better mold the flow of light, or photon management as it's sometimes called, so you want to bring light into something, like in photovoltaics, you want to bring light out of something, like in solid state lighting. They're getting to a functionality significantly below the wavelength could be interesting. To miniaturize and integrate further, so just the catchwords right here, sensors in the very first place, and a few others. And well, the last point, for me personally, honestly, maybe the most important one, simply to understand what happens there, and of course, simply for the fun of it. Okay, so now let's use either photons or electrons or any combination of it. Photon in, photon out, or photon in, and if the photon is absorbed, no photon out is maybe, of course, the most evident, in some aspects, the simplest thing that you can do. So elongated gold particles now excited along their long axis, shown in this scattering spectra, single ones. So they were fabricated by electron beam lithography, and you see rather broad resonances, but very sensitive to shape. Okay, so you make these particles a little bit longer and you see a red shift, so a shift to lower energy of the plasmon resonance. Now, this can be quite easily understood because the further apart the surface charges are on this nanoparticle, the less they are restoring Coulomb force. Okay, so you have a weaker restoring spring and you have a red shift. So quite evident. You can then look at particles, in this case, many particles. So these are measurements from an array, not from single ones. But if you couple two particles together, if you bring them closer and closer together, and here not the whole spectra are shown, but simply their resonance position, and what happens in one direction, namely in a horizontal direction, is that you have a shift to the red, and in the perpendicular direction for the maximum of the signal here in the spectrum, you have a slight shift to the blue, so to higher energy. Now, why is this? These two dipolar particles are simply two coupled oscillators in this case. And if you bring them close together, according to the two directions, you have either an enforcement of the restoring force leading to the high energy solution, or a weakening of the restoring force leading to a low energy solution. And it's perfectly what we would expect from two coupled oscillators. So this just to emphasize control shape, but control shape on a nanoscale, right? And of course, the position of the individual structures to really be able to control the optical properties. A next point I would like to make is control material properties. Of course, this is easier said than done because, well, I can easily control the geometry, but if I have a given material, it's hard to control it. But nevertheless, we can control to some extent with temperatures, with rates, when we have evaporation deposition approaches, the granular size of a metal. So the polycrystallinity can be described by larger particles or by smaller particles. And so, for example, here we have the real part of the permittivity that we know already now from gold over the spectrum, and it gets more negative as we go to higher wavelength. And you see by simple temperature, relatively moderate temperature steps in annealing, you can change that, as we know from ellipsometry. And this has then immediate consequences on the positions of the spectra. And if you want to do specifically something with the spectral positions, like in this case, it was meant for Raman spectroscopy, then this is important, right? And if you do it right, you can maybe end up that the annealed structure for one particle sits precisely at the wavelength of the non-annealed structure of another particle, and then you can begin to play around with the comparison of the different parameters that are involved. Of course, as I said, there are limits to that. What is small is quite often very fast. So the plasma oscillation, the plasmon oscillation, if you induce it, consists of this delocalized charges. And it's one quasi-particle that is effectively having a certain lifetime that describes your electrons that are oscillating. And the dephasing time in a typical metal for typical structures is in the order of a couple of femtoseconds or a few tenths of femtoseconds. And one of the advantages, again, when you can control your geometry, is that, for example, you can look by time-resolved methods, right? You can look at the lifetime that basically you see here. So this is the exciting pulse, and this is the plasmon lifetime that you have right here. You have a higher electric field intensity because you have a resonant phenomenon, right? You find, in this case, 6 femtoseconds for these gold nanoparticles. And if you now change the shape of the particle, you get a beating because your resonance frequency is different from your exciting frequency. I've set them now apart, right? But nevertheless, if we fit this beating that we observe here from the experimental data, again, we have, of course, the 6 femtoseconds. But you see, you can play on a very fast and very small scale with the dynamics of the system. And you can use your near-field optical microscope, of course, if you are very motivated and you go along. So it can look like this. This is just a sensor that measures actually the distance of this particle. This is a sharpened fiber tip that you have right here. And if you look at individual particles or particle chains of roughly 100 nanometer diameter gold particles, you can either see at first view something that is, well, not so convincing because, well, you have two lobes here that you see optically around your particle, and that's nothing else than the dipolar character, right? The dipole field of your particle. It's asymmetric here because the illumination of this nanoparticle was asymmetric. But nevertheless, it's quite large. And you could argue if this is 500 nanometers here, this scale bar is valid for all panels. Well, that's the resolution apparently of an optical microscope. So why bother? But we were using here a purely dielectric fiber tip to scatter light, okay? And while the foremost position, the high curvature of the fiber contributes the most important signal, it's the whole body of the fiber that coupled, because we did not metal coat or something like that. Why not? Because we wanted to have a comparison with theory, and we know that it's very close to non-invasive, right? So just a small dielectric dip doesn't change the system to be measured too much. A metal-coated dip does, okay? That goes back to what I told you before already intuitively. We assign a stronger optical impact, a stronger optical response, of course, to a metal structure than to a dielectric structure. But luckily, we simply decided also to look at this row of particles, because in this row of particles, the neighboring particles couple. And if you compare them here horizontally, you see now we see most of the field, the near field, in between the particles, right? So it's just like in a capacitor where the field sits in between the electrodes, and this coupling squeezes the near fields, okay? So it really concentrates them to the region in between the particles. This was just a lucky strike because a single particle has a huge field, okay, that simply strikes out, and near-field microscopy is not too convincing on that, as I said. But if you squeeze your lights, you force them in between, and this was the proof that indeed the near-field optical microscope can measure locally then that on the scale of, let's say, around a tenth of the wavelength. This was actually done really long time ago. Yeah, excuse for that. But let me just now emphasize that this is kind of ongoing, and near-field optical microscope can be a fantastic tool. And nowadays with better optics, but especially with quicker electronics and some computing, you can not only measure intensity in each and every position, but you can measure a whole spectrum in each and every position. And you can measure spectra in different directions, right? So this is a very interesting approach, because in each and every point you have information about the intensity, you have information about spectral changes, okay, so about shifts of the maximum position. You also have information about shifts, about the width, and so on and so forth. So you can really go multi-channel with local measurements, and maybe also think a little bit about the role of the tip in, after all, it might be small, the influence, but after all, influencing the system, so that you measure a coupled system of tip and sample. You can go on. Let me just go quickly over that and look with a near-field optical microscope on wires. Now it gets a little bit boring just to look at gold structures. So we can, for example, add now quantum dots to go a little bit hybrid. Okay, not as much as Oliver Benson did, but for example, we choose colloidal quantum dots to put them on specific positions to couple their emission to plasmons, to excite plasmons with that. Of course, we do the same thing, that we can really tell we have individual quantum dots there. We can count single photons, time tag them, then either look at their lifetime, or really prove with the anti-bunching signal that we have single ones there. And then we can, for example, look at systems like that. Okay, so we have wires. In this case, it was plasmonic silver wires. And we have one or two or three. This was difficult to say. I mean, in this case, it was evidently one, but in some other experiments, it was two or three colloidal quantum dots, and they were positioned in this case with multi-step electron beam lithography. So first you make your metal structure, and then you go again to the lithographic system, and with a little bit of luck and good equipment, you find back to a couple of nanometers your initial positions again. So you can, for example, really put it here. You see already what happens. You see it here in the lifetime plot, but also in the anti-bunching plot. Your lifetime gets significantly reduced. That's simply because the local density of states, as I argued before, is higher here. But you can also, by going with the laser spot here over the end, either excite your quantum dot and then see if you're in the right position, some plasmon emission here at the end, or you can launch your plasmon, and again, if you do it in the right position, you have the brightest emission now from the quantum dots here at this end. So that can be combined and actually be done. Okay, so much for photons. Now let's stay with photons that go in, but let's look at electrons that come out. You can use your femtosecond laser that you have from the ultra short experiments before, but now to use it to really provide high intensity, right? To provide high fluence and to get electrons out. Okay, to photo emit electrons, and for that, with a typical femtosecond laser having pulses in the infrared or near infrared regime, typically you need 3 or 4 photons at a time. But well, that can be done. And then, as we learned, when we look at the energy of the electrons that fly away, right? If we do spectroscopy, for example, in the time of flight spectrometer, we can learn something quite interesting. And this quite interesting is that we know from measurements that show us photocurrent versus light pulse intensity or light intensity, that we have a 3-photon process. So the energy with which our photoelectrons arrive at the detector is to be expected to be very close to zero, or between 0 and 1 electron volt. But you see, depending on where we are with the resonances of our particle, this here is the laser spectral range. And if we are in resonance or off resonance, or if we have bow ties, so two opposing triangular particles with a supposedly quite strong field in the middle, we get energies up to 20 eV, 20 electron volts. The highest energies for these bow ties, and then for the resonance, and so on and so forth. So apparently something with the plasmon field is acting on the electrons. And indeed, what we have is, in the strongly inhomogeneous, exponentially decaying plasmon field around the particles, we have an acceleration of our electrons, right? So the electrons are strongly accelerated up to 20 electron volts. Seeing that from the point of view of, let's say, quantum optics, that means the electron, while flying away in a very short time, in fact, because the distances around the particle are quite small, is absorbing up to 20 virtual photons from the plasmons. That means I have to have more plasmons than one in my particle. So this is really quite interesting physics on a very small scale, and you can tune the properties of the accelerator, so to say, by tuning your particle. You can have all kinds of looks, close looks on that. You can vary the energy and so on and so forth, but I simply go over that and would like to show you this. This is simple simulation, and although we did that quite some time ago, follow-up experiments prove a little bit tricky, but we are still, after all that time, working on it, because I simply think it's so interesting that you have the first and strongest acceleration, right? So here you have the energy of a particle depending on the position around, sorry, the energy of the electron depending on the position around our particle. The strongest acceleration, the most important one, is happening in a couple of femtoseconds. Actually, the highest energy electrons, and this is in agreement also with experiments that people do in photoemission from tips, from sharp tips in vacuum, is the highest emission probability happens when you have the highest field intensity on the surface of your particle. So I get the particle, the electron out of the particle, but then I'm already very close, because it happens here at the maximum, to the electric field turning around. So the period that now leads to the electric field vector pointing towards my particle. And indeed, these high energy particles, or relatively high energy particles, come back, as we assume from simulation, to our particle, are reflected, and then are already with their reflection energy at the perfect position now to be in phase, accelerated with the next period of the plasmon field. As I said, this is just simulation so far, but to measure things like that on a very small scale, this is, I think, really something quite attractive. Okay, and I think I jump over that. If you have external photoemission, what I talked about now, you can also have internal photoemission, and so photocurrents on a very local scale. Again, here from colloidal quantum dots in electrodes is something that I think also will keep us busy for some time. But I'll jump over that and would like to come to now a combination where we leave away photons completely. So we have an electron in and we have an electron out. And in fact, this is something that dates back quite some time. In fact, this is the method with which surface plasmons were first experimentally evidenced. And this is a seminal paper by Powell and Swan from 1959. They looked at the energy of electrons that were reflected from aluminum surfaces, right? And if you do that, you find these peaks here, this, that, and this is just the fundamental, so the energy of the bulk plasmon, so of the volume electron oscillation, and multiples thereof. Okay, this was well known at the time, and it was well known that this happens at 15.3 electron volts. A year before, it was proposed by Ritchie that there is this surface plasmon energy as well, okay? And it has something to do with the square root of 2 with relation to the bulk plasmon, and it should be for aluminum at 10.3 electron volts. And indeed, here it is, and multiples thereof. Okay, so this was the first experimental evidence with electron energy loss spectroscopy on surface plasmons. By the way, 1959, well, I was not born yet, but I can imagine it. All our younger colleagues probably listening, for those, it will be way back in the dark of history. But let me assure you, Cedric Powell is up and well, and he's running as usual. Just to be also up to date, I checked his homepage just before, and you see his latest publication dates from March 21. Okay, just to be sure. So he's still working. It was then a couple of decades until, let's say, this paper by a group from Orsay in Paris, in France, in 2007, that EELS was coming back to plasmons. Or it has always been there with bulk plasmons and surface plasmons, but not with higher energy or lower energy losses, sorry, to lower energy regimes. And with better spectrometers and especially higher, better analysis of the data that you have. It was this paper from Nelaya et al. That first showed here, this is a triangular particle, you see sub 100 nanometers, and they showed a series of resonances, of plasmon resonances in this particles. So you see here just the reconstructed energy loss in one of them. How can you do that with electrons? In fact, people who are into electron energy loss spectroscopy or EELS, for them, it has always been evident because there is a so-called loss factor, and the loss factor includes, guess what, the permittivity of the material, and with that we are back at the optical properties. In fact, what an electron does is it zips by our structure or even zips through with a very high energy, so it's a kind of delocalized charge distribution that you can use here as a description. It's a very broadband excitation though, and it can excite a broad range of plasmon modes, or all of them. And then if it has excited them and it flies away, it has to exert force against the field. Okay, and this force leads to the loss of energy that you then can measure in a spectroscopy setup. And you can do that, for example, like this. So you scan over your surface, and in each and every point you take a spectrum, and then you can either get out your spectra, or you can simply cut out an image at a given loss energy and make images of your mode that you have there. That can, for example, look like that. So this was one work we did in morphing. So to say morphing a round particle to a triangular one, there's lots of going on when you do that, because if you make your particles a little bit larger than just in the dipolar limit that I was using so far, you don't only have your dipole, you also have higher multipoles, you have a quadrupole, a hexapole, and so on and so forth. And it's really good fun if you do this morphing, for example, to look what happens to a quadrupole if it's forced to live in a triangular particle. So you have all kinds of energy switches between different modes and so on and so forth, but that's not the main story. The main story for me is simply you can calculate, in this case, the charge distribution of those modes, but we can also measure them with a high resolution. It's a discussion of its own how high the resolution actually is. Of course, your transmission electron microscope in which you use this electron spectroscopy has angstrom resolution, but you have, of course, a kind of delocalized interaction when you have this Coulomb interaction between an electron that flies by and the mode structure that you look at. So let's be careful there, but let's say we have a spatial resolution of a couple of nanometers, and nowadays we have energy resolution in terms of, let's say, routinely 100 milli-electron volt, but there are now also nice systems around that actually deal with 10 milli-electron volts, so you can now make also nano optics with the electron microscope looking at vibrational systems, doing vibrational spectroscopy, in fact. Okay, and you can do things like that. This is an aluminum nano triangle, really looked at from the infrared, 1 electron volt to a couple of electron volts. And you see just that is measurement, okay, that is pure measurement. It is really a system that allows you to approach all the mode content that you have in your system under investigation. A final point to EELS, people in electron microscopy have developed wonderful things in recent years, especially they have pushed further the three-dimensional reconstruction of structures. So you look at a nanoparticle, for example, and that's even working with atomic resolution. You look at a nanoparticle and by making tilt series, so by looking at the images at different series, you can then tomographically reconstruct actually the shape of the particles. So for example, here we have nanoparticles that come out of lithography. It looks pretty horrible. But for example, this feature here is really fantastic, because what you can now do as well is, apart from topography, also looking at EELS, and thereby looking at the plasmon mode patterns, right? And this small feature here that is a defect, as I would call it, but is apparently a very small curvature thing that features a local mode and thereby a very high local field intensity right here. You can look at different modes. This is now 2 particles on top of each other with a dielectric spacer in between. And you see you have either the bonding, so plus and minus on opposing sides, or the antibonding, so like charges on opposing sides of this small gap. Okay, so I clearly approach my timeline coming close to a finish. Is 5 minutes okay? Yeah, okay. So I try to come to an end within 5 minutes. What's missing now is you insert an electron and you get a photon out. Okay, so that's usually what we call cathodoluminescence. And we again do that because we aim at high spatial resolution in a transmission electron microscope. First of all, let's put that a little bit in context, because after all, doing optics and comparing measurements and complementing measurements like that with optics is of course still a very important thing for us. And I would especially like here to point out Garcia de Abajo and Mathieu Kosiak in either ICFO close to Barcelona or in the Orsay in France, that really push this field. What I want to underline here with this slide is, when you ask what actually compared to conventional optical signals do you see in EELS, I would say you see optical extinction, extinction being the sum of absorption plus scattering. Okay, and indeed, if you try to express the EELS loss function, at least in the limit for a small sphere, okay, so just dipolar term, you find the same expression, the dependence on the volume and the imaginary part of the polarizability in the Eels loss function as you find it in the extinction cross-section. Okay, so Eels is very close to what we find in extinction. For the specialists in the audience, I should add, you can only measure fields that are oriented along the electron trajectory in Eels. Okay, with three-dimensional topography, you can overcome this problem, but this is just an important limitation. On the other hand, if you think about cathodoluminescence, in cathodoluminescence, you excite whatever you have in your system, in your sample with a fast electron, so no problem in exciting everything there. But to get a photon out, the symmetry of your mode must be able to couple to propagating light fields. And that's sure enough a limitation, okay? And indeed, as you find again here in this correspondence, what you have in CL is a very close correspondence to scattering, to optical scattering. And this, for example, you can use to learn about, for example, how a dark mode, so a mode that is not coupling to light, is developing into coupling to light. If you make your nanoparticle larger and larger, that retardation begins to feature this coupling because higher multipolar modes begin to become important. We actually use in a disk-like nanoparticle the so-called breathing mode, so the mode that has simply an in-out oscillation of particles, okay, in a radial manner. And because this is a pure radial manner, the overall dipolar moment of this particle is zero, if you're small enough. If you're getting larger, you begin with retardation to be capable to couple to light. And this is what comes out. If you look at the Eel signal from a small disk to a large disk, that doesn't change too much. If you look at cathodoluminescence, yeah, you begin to couple to light. So your particle, your dark particle begins to light up. And this for us is important because we want to be in a certain range of coupling to light for certain applications. And as we know that now, we can begin to apply that in further systems. And to finish, something that we did only very recently, also to emphasize there are limits, and we know these limits, and we have to know these limits. We were desperating a little bit. The story began like this, by looking at spectra again from a disk, right? At cathodoluminescent spectra, we had this wonderful system that allowed to detect spectra from both sides. And the spectra were always shifted just a little bit, okay, below 10 nanometers. So of course, first you argue there's something wrong with your detection system, and then you check and check and check, and everything seems all right. In fact, it's not, because it's a built-in limitation. Your electron beam breaks symmetry. It comes from one side necessarily. And as it zips through the particle or by the particle, it necessarily introduces a dipole moment by featuring different densities on the upper interface and the lower interface. And this dipole moment interferes with the mode emission. We are talking about cathodoluminescence under investigation, and this interference gives rise to the spectral changes. Okay, I would simply like to stop just here, and with this list. Again, if there is only one take-home message, I hope there are more, but if there would be only one take-home message, it's use your photons, use your electrons, combine them, whatever is good to have. I would also like to emphasize just with that, of course, you know, there are many people working on all these topics, especially cathodoluminescence and Eels. Let me also, because we are there, even if we are only virtually there, mention the wonderful collaboration with colleagues from Brunner. And well, I of course thank all the people that have contributed. I thank you very much for your attention. let me already here wish you all the best for all the workshop. I'm happy to take questions, and I think I've also posed a few questions myself. So thank you.
So with this, I would like to open the discussion. Is there anyone who wants to ask a question? Yeah, I don't know if you can see Joachim, but many people are clapping their hands virtually.
Thank you very much. My pleasure.
So if anyone wants to ask, please write a question in the chat or use your microphone and shout it out loud. Don't be shy. In the meantime, this might be a bit tricky question, but I was wondering, for you personally, which of the four photon and electron combination is the most interesting one?
You are absolutely right. That's a very tricky question, but a very good one. Yeah. Well, difficult to say. I simply find this eel stuff really, really crazy. Yeah, because it works on better energy scales. Of course, it is also true for the other methods. But let's say these eels, especially because I myself have actually, as I have to admit, no idea how to operate a transmission electron microscope. I'm awed by these systems, but because it's also going back so far in time with the application to plasmons. Okay, let's pick eels.
Thank you. So the questions are still not coming. I don't know if anyone's waiting to ask something. If so, please raise your voice or hands. Okay, here's a question from Tomasz Sikola on photon in electron out situation. So for the cathodoluminescence, what was the energy of the photoelectrons which were measured?
I think you still see my screen, right?
Yes, we do.
Okay, so I think this refers to the photoelectrons from these experiments, right?
I'm not sure. Maybe Professor Shikola could turn his mic on and tell us what exactly he means.
Let me just look in the, I think I read photoelectrons.
Yeah, there was the photoelectrons, but
okay, so I stay with that. That was a very simple time of flight spectrometer. So we simply, or our colleagues in this case from Wiener Research Center in Budapest, have in vacuum this time of flight, and depending on the electrode potential that you have in there, you can deduce the energy of the electrons that you have.
I'm sorry because I wasn't able to unmute. Yes, so sorry for that. Okay, yeah. Okay, so it was measured some LEAM or photoelectron microscope or something like that. And you measure the energy electrostatically by some grids, or how was it done?
It was electrostatically, right? Yeah. So you have a kind of potential that you can vary, and you simply along a straight line in this case measure the arrival time of your electrons, and that gives you the energy. But you're absolutely right. You can as well use the standard systems that you have in a beam, for example, and simply deviate them in the usual hemispherical deflectors.
Okay.
It's not critical how you do it here.
Yeah.
So there's another question in the chat from Bruno Hub, which is on one of these slides there was electron energies outcoming from structures emitted by the laser. Why the electrons emitted by the blue shift laser have lower electron energies than from the redshifted?
That's an excellent question. Very good observation. I, by myself, only pointed out that if you have the highest expected resonance here, or the highest expected field, you have the highest energy. Then if you're in resonance, that comes second. And then you are here to a roughly same extent to the right and to the left on this wavelength scale. But you see you differ here by a few electron volts. Actually, it's a combination of the material properties and the field strength, but this we only deduce from simulation. We never really found a good convincing one sentence answer for that. It's a combination of all the properties that you have in there and that we have a wavelength scale rather than an energy scale and so on and so forth. But it's an excellent observation, and well, I have to go a little bit out to answer that, as you realize.
Okay, there's another question. What about the interfaces such as low angle grain boundary and the high angle, and how do they affect plasmon response and extinction spectra? And then what is the role in twinning in plasmon response?
That's also a very good question. In fact, I was, when we were setting out to measure things like this, I was expecting to find a much higher impact of actually the number of grain boundaries, but actually it's a quite weak influence. And we only know that there is the expected dependence, less grain boundaries, less damping. But because the effect was so small, we stopped actually at this point and never had a closer look, leave alone to learn about twinning impact and these things. So actually, I don't know. It's not really very important. There is one exception, though. If you really get very, very small with your grains, then things change dramatically. But this was nothing that was done by our group. In one sentence, why would you wish to really get very small in the grains? Simply because basically the size of one crystalline grain limits the smallest features that you can fabricate by lithography. Because if you make a mask with the electron beam and then you evaporate, and you have thermodynamic boundary conditions so that your average size of a crystallite is 20 nanometers, you have no chance to have a curvature, for example, that is smaller than 20 nanometers. Now, what you can do is change the thermodynamic boundary conditions and, for example, evaporate at low temperature. It's quite easy. You simply put a cold finger, you put nitrogen, okay, and you evaporate at that. Then you get really small grains, but then it begins to be highly damped. And people have done that, but actually it's nothing I have readily at hand to tell you numbers.
Okay, there's one more question on cathodoluminescence, which would be that you show the shift in the cathodoluminescence spectrum, which comes forwards and backwards with respect to the E-beam. And the question is, how does this shift depend on the thickness of the nanoantenna?
Only excellent questions right here, yeah. The thickness of the nanoantenna is very important, because if you really go through here in the middle position, and if you want to effectively excite the breathing mode that we were also using here, you have to go in the middle, okay? You have to go through the metal. And the thicker the metal is, the more difference in the excitation of the surface charges between the front and the back interface you will have. And the higher the induced dipole moment will be. And this induced dipole moment, as I said, then has another phase dependence and thus can interfere differently in forward and backward direction. So it's important, and the effect gets stronger when you have a increased thickness right here. I think we have we have parametric studies and also including this point in the supplementary info of this paper.